So a review of the integration methods that we have done so far. There's only 2 of them. What are our 2 integration methods? Come on. Use substitution is our second one. And what do you look for, or when do you use substitution? What does it look like? What does the integram look like so that you try to use substitution? Jackie?
We see a function as derivative.
Sure. We're looking for a function and its derivative. It could be in the form of a quotient. Right? We did a lot with logs, natural logs. We were able to use substitution on those when there was an x in the denominator. It could look like a product. Such as the integral of sine x cosine x dx. That's a product, but I do see a function and its derivative. Okay? So the other thing that I would say you can use as a key to try use substitution if you see a composition function. Okay, a function within a function. All right, what's the other rule? The basic one. Easier. How do you integrate x to the fifth? It's simply the antiderivative, but I would just call it power rule. Right? All of these are antiderivatives, so I would just say the power rule. And when do we use power rule? I just gave an example, like x to the fifth. Polynomials are a good example of when we can just simply use power rule. Okay? All right. Well, certainly these 2 situations do not encompass all of the possibilities. So, today we are going to learn a method called integration by parts that is another method that's very useful when we have a product. Okay? So, first thing I want to do is actually show where our approach comes from, and then we will use it. All right, so if we were taking derivatives of a product, what do we need? What rule of a product? Product rule, thank you. We would need product rule. And that's actually where we begin to come up with our method for taking the antiderivative or integrating a product. So let's look at the derivative with respect to x of p times b. So what would that be? First times derivative of the second would be p times, and I'll write it as db dx, plus what? Thank you, b times dp dx. All right, we're going to use this as our starting point, but before I show you how we do that, let's look at an example. We are going to be doing this integral in just a minute, which has a product, x times cosine x. Could you use substitution on that? Do you see a function and its derivative? No. So we need another method. And what I want you to realize is I could think of this in terms of p and b as 2 things being multiplied together. I could say that I want to call this xp, that's my p function, and this cosine x dx is a differential, it includes dx, so I could call that db. So if I can find a way to integrate the form, the integral of p db, then I would be able to find a way to integrate a product that will work for some integral. All right, so to get to this is what we want to find, some way to integrate that integral of p db. And what I have is d dx of pb equals p dx. You've already written this, I just am going to write it a little lower, plus b dp dx. And since I want to get to an integral, I'm going to integrate both sides of this equation. So let me change the color a little bit. So I'm going to integrate each part. Sorry, my pen's delaying a little bit here. There we go. There we go. And we're going to integrate them with respect to dx, with respect to x. So each of these will get a little dx after that. Okay? Well, what is the antiderivative of the derivative with respect to x of pb?
PB.
It is pb. They undo each other, so here we get pb equals, and here, if we think of this algebraically, what happens to my dx's there? They cancel, yes? Because I have a dx on the bottom and a dx being multiplied, so this is the integral of p dv plus the integral of what? b dp. All right, well, we said this is the thing we want to learn how to integrate, so I'm going to isolate that. The integral of p dv would equal what? dv
Minus integral of b dv.
Good. Oh, wait. dv minus the integral of b, sorry, this should say dt. There we go. Thank you. It should say p, p, p. There we go. Start. This is the form, or the format that we use for integration by parts. Generally, it's not written with P's and B's, usually written with U's and B's. It's just that my U's and B's always look very similar. So I'll write it that way just so you see it. The integral of U dv equals UV minus the integral of V dv. Those are the important lines from this slide. And now, we will see how to use this format to solve for the integral of a product. You'll learn two ways to do it. I'll show you the traditional way first, and then I'll show you what's called the tabular way. And I have not come across a problem in which the tabular form has not worked for any reason. It's just another way of organizing the information, and it's much cleaner.
Does this only work for products?
Yes. All right. So your problem, your integral has to fall in the form of this u dv, which is two functions times each other. So let's take a look at our first one. So as I said, we're going to be solving this integral to start. It is a product. U substitution is not going to work. So we start going through our methods. Generally, we look for power rule first. We look for U substitution second. Then we go to integration by parts. So to do this, the integral of U dv equals UV minus the integral of V du. Well, if our answer is going to be UV minus the integral of V du, that means I need to know what U, V, and du are. That's a V, not a U. So we need to identify and pick our functions and our functions that will match U and dv. So the first thing we will do is identify U and dv. Now there's different types of problems we apply integration by parts to, and there are different ways to choose your U and dv. And the first one we're going to look at is choosing a U such that if I take the derivative repeatedly, it will go to 0 quickly. So choosing a u such that the derivative goes to 0 quickly. So if I'm looking at x and cosine x, and I'm thinking about taking derivatives, which one of those goes to 0 quickly? X does. So our u will be x, and our dv is everything that's left, which is cosine x dx. Okay? So from there, I need du and I need v. Well, how do we get du? We take the derivative. So what is du? 1. Actually, 1 is du dx, but we would move the dx over, so it's 1 dx. And to get v, we integrate. What is the antiderivative of cosine x? Sine x? And it would really be sine x plus v, right? Okay. I'm going to tell you now, and I'll show you as we go through it. You don't have to write the plus b at this point. With integration by parts, save the plus b to the very end, because if I did plus b here, it would drop out and cancel out in the process. Okay, and we would just have to put a plus b at the end anyway. All right, so now we set up our solution in the form of the right side of our integration by parts format. So uv would be what? Would be x sine x minus the integral of v du. Our v is sine x. Our du is 1 dx. Okay? So why is it helpful to have this? What's the deal with this integral of sine x? Do we know how to take that integral? It's an easy integral, right? So now we have an easy integral to solve. So we have x sine x minus, what is the antiderivative of sine? Negative cosine. So we get x sine x plus cosine x plus c. And there is our solution. Now, a couple of things I want to talk about. First off, this integral that we ended up with here, the integral of sine x dx, that was a very easy integral. And we knew how to take that antiderivative. That was no problem. But sometimes when you use integration by parts, when you subtract this integral, it's another integration by parts. So where it would be another product. So again, you would have to choose a u and a dv, and find your du and your v, and do integration by parts again. So there are many problems like this that require repeated integration by parts. So that's when this tabular form really is most useful. So we're going to do the same problem using the tabular method. So we can see how it organizes the information just slightly differently. So same exact problem. And we are still using integration by parts to solve it, but the setup is just slightly different. So we still want to choose a u and a dv. And the method for choosing u and dv, still the same. In this case, we want to choose the u such that the derivative goes to 0 quickly, so we'll choose x. And the dv would be cosine x dx. Generally, when I use the tabular form, I don't write the dx, because I just want to keep it as two clean lines of information. Technically, the dx is there. Okay? All right, so what is the derivative of x? And the derivative of 1? 0. So, the left column, we do derivatives. The right column, we do integrals. So the antiderivative of cosine x was what? sine x. Antiderivative of sine x, negative cosine x. All right, and now we set up just some lines to help us see what is going on. And we're going to draw our line from the top left to the second on the right, so just diagonally down. And then when we choose to draw the horizontal line, what that means is we are integrating back. Sorry, that should be a straight line. Okay, whatever. Okay. And we'll have a plus, a minus, and a plus. We always start with a positive, and then we alternate signs. Now let me tell you what's going on. Let's think about this. Our solution integration by parts was u v minus the integral of v du. Well, this is u, and this is v, correct? Minus the integral of v du is what we get on the next diagonal line. Okay, so it's just reorganizing the information. So, please make a note, when you do a horizontal line back, we are integrating, because that's going to be the repeated minus the integral of v du. And we need to note that anytime we're working with these lines in our tabular form, we are dealing with products. We are multiplying on those lines. All right, and so the reason I drew my arrow back here is because I got to 0. So in the table, when we choose such that the derivative will go to 0 quickly, we integrate back on the line where we have the 0. So let's see what this means. What is this telling me? So my solution is x sine x. We multiply the two ends of the line here, so x sine x. Then we will have the product of 1 and negative cosine x, and we have a negative here. Negative times a negative is a positive, so plus cosine x. And then we will have minus negative times a positive, the integral of 0 times negative cosine x. Sorry, I took care of the negative already. Dx. Well, what is the integral of 0? What's the antiderivative of 0? In there. C is a constant. So what we have here is x sine x plus cosine x. And we could write it as minus c, but generally speaking, we deal with positive constants, so we would write plus c. And there is the same solution we got when we did it the traditional way. All right, I'll make a couple of notes here. We always integrate back on the horizontal line. And example 1, we choose u to be an easy derivative. That goes to 0. All right, so let's see some other examples. Questions on the actual method, the organization? Yes, Fred?
Where are you getting dv from?
So dv, first, we choose our u, and everything that's left up here is our dv, cosine x dx. And then, to get the next one, we take the antiderivative. And then you take the antiderivative again. You're just taking an antiderivative each time. You're doing integrals. And on this column, you're just taking the derivative each time. Okay? So the antiderivative of cosine, if I integrate cosine, I get sine. If I integrate sine, I get negative cosine.
What is v? How do you get a v?
So u and v, well, what we do here is we want to label this original problem in terms of u and dv, two things that are multiplied. So our u is x, and our dv is everything that's left. To get v, we take the antiderivative of dv. And the reason we want to do that is because we need that for our solution. We need to find what v is. Okay? Question over here.
Oh yeah, I was going to say, so the horizontal line always has to point back to 0.
No. No. So this is our first type, and in this type, it is a nice time to integrate back because there's always going to be a constant. Okay? So you'll now see other types where we integrate back at different times. Okay, Manav?
So you just to be clear, you want to integrate that when it's a constant regardless of the number that's on the.
You want to integrate back when it's an easy integral to figure out.
Okay.
That's a nice way to think about it. I mean, when this comes out to be the integral of 0, that's a very easy integral to take. You can integrate back anytime you want, but your choice would be when it's easy. Okay?
And it's most common, like, the one that's the lowest on the U table. Like U is the lowest, right? Like you're taking the integral each time.
It's one type of method, there's one method that we're showing here. You'll see, let me show a couple other examples and it'll become a little more clear. All right, so let's look at this one. Now, if we were to do this one the traditional way, choosing U and dV, which would you think to choose for your U? Which one goes, so the only reasoning we have so far is pick a U that goes to 0 when we get the derivative. And so which one would that be? That would be x squared. And that leaves my dv to be everything that's left, which would be e to the x dx, and we just don't have to write that dx. Okay? So, left column, we just do derivatives. The next one would be what? 2x, then 2, then 0. So it gets to 0 pretty quickly. Not too bad. And the right column will be very nice. The antiderivative of e to the x is e to the x, e to the x, and e to the x. So I'm stopping here again because I got to 0, and it would be an easy integral. Okay? Think about this in the traditional form. Each one of these extra rows is another time that I would have to do integration by parts, using uv minus the integral of v to u. So it would be multiple layers of integration by parts in the traditional method that we can do very quickly using this table. All right, so let's set up our line. And get our signs right. uv is positive minus the integral of v to u, and then it would just alternate. So now, anytime we end up with our integration being the integral of 0, that's just going to be a plus c, correct? Because the integral of 0 is a constant. So you don't have to show that integration. I'll show it one more time here, but you don't have to show that every time we have a 0 on the bottom row. So what is our solution now?
Squared dx
X squared e to the x.
minus 2x dx.
Plus
Plus 2
e to the x minus the integral, because the horizontal is always integration, of that product, integral of 0 dx.
You can just do the constant, right?
So now, I can say x squared e to the x minus 2x e to the x plus 2 e to the x plus c, because this will come out to be a constant. And now, in the future, you don't have to write this integral form. Your last integral is the integral of 0, then you can just write your plus c. Okay, and we're done. Questions on that one? People are still writing, so I'm going to hold up a minute. All right, so now let's look at one that looks a little bit different. E to the x cosine x. So just like with u substitution, we had to become more comfortable with choosing our u for u substitution. Here we have to come up with our little methods for choosing u and dv. So, all we've done so far is chosen our u based on the derivative going to 0 quickly. How's that gonna work out here? It's not. Neither one of these would go to 0 quickly. So here is one where what I want you to look for is, sorry, my pen's stuck, is a repeat of the original integrand. So we'll write a little note, look for a repeat of the original integrand. So we're looking for a line that has e to the x and cosine x, and it does not matter if this one is positive and this one is negative, or this one is negative and this one is positive. It makes no difference. We just want to see that repeat of e to the x cosine x. So, on this one, your u and dv, it does not matter which one you choose, because neither one of them gets simpler. Sorry. So let's choose e to the x for our u. Oh, that's crazy. So we'll choose e to the x for our u, and we'll choose cosine x for our dv. All right, so what is the derivative of e to the x? That is also e to the x. And what is the antiderivative of cosine? Sine x. Next derivative is e to the x. Antiderivative of sine? Negative cosine. Do I need to go any further? There's my repeat of e to the x and cosine x. So let's set up our line here, here, and here. So that's not an easy integral, but in this case, we are never going to get any kind of different integral. And so by looking for a repeat, it allows us to use some algebra to solve this. So when we're doing one like this, I always want you to rewrite the original, the integral of e to the x cosine x dx equals, and my solution will be what? E to the x sine x, and what? Plus e to the x cosine x, then? Minus the integral of e to the x cosine x. So we end up with that equation. Yeah, Matt?
How does he know where to stop? You're not going to zero.
Right. So in this one, I'm showing you a brand new type. And when you have two cyclical derivatives and integrals that won't go to 0, you can look for a repeat of the integrand. So I stopped because I saw e to the x cosine x, which is what I had in the original. And I'm going to show you why now. That's helpful. Yeah, Frank?
Negative cosine.
That's where the minus came out here. I just pulled it to the front. So I could write it as plus the integral of e to the x times negative cosine x, or I could just...
I meant like in the first part, so you match the u.
Oh, I said it does not matter whether it's positive or negative. Yes. So these, we're just looking for a repeat of cosine x and e to the x. These do not matter.
When you're putting the signs in the table, is it always positive, negative, positive?
Yep.
Starts with
It
positive?
always alternates. Starts with positive because in our solution for integration by parts, it's uv, which is a positive value, minus the integral of v du. So this is uv, and this is the integral of v du. And then it's the repeated version of that from there on. All right. So can anyone see how I can solve for the integral of v to the x cosine x here? It is just an equation. Can't factor it out. What if I had solve for x? What would I do, Jake?
Add it to that side.
Exactly, I would add the x over to this side, right? So I can do that with that integral. That's the same exact integral that I have over here. So I can add plus the integral of e to the x cosine x dx to both sides of the equation. And I now have 2 times the integral of e to the x cosine x equals e to the x sine x plus e to the x cosine x, and then what? Divide by 2. Cancel them here, and now put your plus once we're at the final step. So now you've seen 2 different types of integrand by parts, or integral by parts problems. One, we look for an easy U. The other, we look for a repeat in the original integrand. Questions on what we did here? Yes.
What would you do if the integral was positive?
Integration by parts would no longer work.
Okay.
Yep, because we would subtract and it no longer would solve for what we're doing.
Okay.
Yep.
We have to keep going until we get the complete.
Say that again.
Because you can't just leave it like that top one, so you have to add it over to the other side.
Oh, right. We're trying to solve this, and it's not solved. You need to get that thing by itself. So we need to do the other. No?
So just like, on the, if it was on the plus, the integrand of EPS, so in that case, will we just leave it there, or?
No, it wouldn't work. You'd have to try a different integration method.
Okay.
You'd have to find another way to do it. Okay. All right. So, but there is a group of problems that fall into this category where this method is useful, and it will always work. Okay. All right. Now let's look at this one. Okay. So on this one, just another practice. U and DV. Try it at your desk, please. All right, so our solution is here. Just be neat and tidy with your table. Okay, now, in the past, we have worked with the natural log. We all know how to take the derivative of natural log. Can anyone tell me what the antiderivative of natural log is? The derivative of natural log is what? 1 over x.
U, ln U.
Close to that. But we can derive the antiderivative of log x using integration by parts. So when dealing with ln of x in an integral, generally you want to choose that to be your u because we know how to take the derivative of it. Okay? So we're going to make ln of x my u, and what's my dv? Just 1. All right, let's go 1 row down. Derivative of ln of x will be 1 over x, and the antiderivative of 1 will be, other way, x. All right, and so this is an example of when I am choosing to integrate back now because the integral will be easy. Right? X times 1 over x is 1. The integral of 1 is very easy to do. All right, so in this case, stopping point to integrate back is when the integral is easy. I could do another derivative. I could do another row, negative 1 over x squared and x squared over 2. Right? I could go another row and integrate back then. Wouldn't be too hard either. But you want to stop at the quickest, easiest point. So we're going to do our arrow here and our arrow here. Plus and minus. So my answer is
X ln
x ln x, then
minus the x
of 1 dx. So we get x ln x minus x plus b. Okay? So even now that we know what the antiderivative of log is, when you've got log in your integral, you're still going to choose u to be your ln of x, because that's a harder function to work with, the one that we just derived. All right, so another example of methods to think about is the stopping point when the integral dv. All right, last one. This one has your favorite thing in it. Inverse trig. Find the solution to the differential equation dy dx equals sine inverse of x. The graph of the solution passes through the point 0, 0. All right, so first off, I am solving a differential equation. Dy dx equals sine inverse of x. How do we solve differential equations? Not yet, not yet. Something we have to do first. We're looking for y. But we've got y's and x's combined here, so the first thing we need to do is separate the variables. So we get dy equals sine inverse of x dx. Now we can integrate each side. Oh, that's ugly. So now we're going to integrate both sides. And the antiderivative of dy is y. And when we talked about this in the past, we showed that we could just manage our constants on the right. We don't have to write a plus c on the left here. And now I will show you that we can use integration by parts to integrate inverse sine. So do you think sine inverse x will be our u or our dv? Phones away, please. Will it be our u or our dv? It's going to be our u because we know how to take the derivative of it. We do not know how to integrate it. So our dv will be 1. Oh dear. And who remembers the derivative of sine inverse? Manoj?
1 over square root of 1 minus x squared.
Very nice. I made the other class derive it. We need to remember to derive that. We rewrite it as sine y equals x. We make our triangle. That's y. This is x over 1. And this is the square root of 1 minus x squared. And then we take the derivative of each side. Cosine y dy dx equals 1. So dy dx equals 1 over cosine y. And what is cosine y up here? Adjacent over hypotenuse. 1 over the square root of 1 minus x squared. I just want you to have this. Sorry, I went through quickly, but I just want you to have this on the video in case you've forgotten how to take that. All right, so back up in our integration by parts, I have that derivative. What is the antiderivative of 1? It is x. Now, if I go another row, is this going to be an easier integral to take or a harder integral to take? Harder. We need to stop now. So we are going to set up our lines like this. And my solution, sorry about that, will be what? X, sine inverse x, then minus the integral of square root of 1 minus x squared dx. What do we do with that? No, we don't stop. We keep going. How do we integrate that? Not integration by parts again. Go through your method. You sub, yeah? You sub, what's my U? U equals 1 minus x squared du. What's du? Negative 2x. We don't need that negative 2, so negative 1/2 du will replace x dx. So I have a negative 1/2 out in front of the integral of what? Our u is under the root in the denominator. That is u to the negative 1/2. Du. Negative 1/2 du replaces x dx, and u to the negative 1/2 replaces 1 over the root 1 minus x squared. So that negative 1/2 sits out in front. Take the antiderivative. It's u to the what over what? Take the antiderivative of this. No. U to the 1/2 over 1/2. Oh, these skills, they disappear over Christmas, over break. All right, so now we have negative u to the 1/2, and our u was 1 minus x squared. All right, so that's what we get for that u substitution. So someone give me my final answer. X sine inverse x. Then what? Careful. Plus, because we had a minus up here, and we had a minus come out of our integral, so plus 1 minus x squared, yep, to the 1/2, and then plus c. All right, you ready for the cruelty? That's y equals, the cruel part is, this has to pass through the point 0, 0. We're not quite done. We need to find the constant. So we need to put 0 in for x and 0 in for y. We get what? C equals negative 1. All right, I told you it's our last one. Y equals x sine inverse x plus 1 minus x squared to the 1/2 minus 1. There is our solution. So you can see where we're going. Sometimes these integration problems are multi-layered. Okay? All right.